This video is about how to create probability simulations using Tinkerplots. Until now, we've been doing descriptive statistics, where the goal was to develop operational definitions specifying how to measure a variety of attributes and constructs. Now, we'll shift attention toward inferential statistics, where the goal is to measure the likelihood of situations that have uncertain outcomes. To begin, create a simple simulation that is like flipping a coin and getting either a head or tail. One way to do this is by selecting balls from a mixer, where one of the balls is labeled H and the other is labeled T. To see how the sampler works, run it 5 times at a slow speed. Notice that this particular sampler selects balls 2 at a time, and that it replaces them each time after they were selected. Then, make a graph of the data, and arrange the data in columns, so that it's easy to see the results. Next, repeat the experiment again, only this time, collect 30 trials, and create a formula to tell whether or not, for each trial, the result is a pair of heads or tails. To do this, create a new attribute called pairs, and use a rule called if, to record whether 2 heads or 2 tails appear. If the first flip equals the second flip, then record this with a 1. And if not, record this with a 0. Now, run the sampler again. And notice how it is easy to add up how many pairs occur after some number of trials. Now, repeat this experiment using a pair of dice instead of a pair of coins. And, for the simulation, use a spinner instead of a mixer. So, the values should go from 1 to 6 for each die. Click Run, and you'll see that the simulation still works. And, if we graph the results, the graph will show how many times out of 30 you get pairs, like 1 or 1, or 2 and 2, or 3 or 3. In fact, it's even easy to simulate a game in which the dice are not fair. To do this, just change the spinner as shown here. Or, you can make a more interesting game by changing the rules so that, instead of just recording matching pairs, you can record the sum of the numbers on the dice for each roll. Notice that Tinkerplots begins by sorting results into only 2 bins. But, if you want more bins, all you need to do is click in the graph and change their size as shown here. Now, let's make the dice fair again. And, let's run the simulation 1000 times. Then, look at the graph. Based on this simulation, what are the approximate likelihood of getting a sum of 12 by rolling a pair of fair dice? Based on this simulation involving 1000 trials, the answer is approximately 30 out of 1000, or 3 out of 100, or 3%. But, suppose that we want even more precision. Then, we could run the simulation 10,000 times. Now, the answer seems to be 279 out of 10,000. Or 27.9 out of 1000. Or 2.79 out of 100. Or 2.79%. How much more precision do you want? A simulation of size 100,000 could be used. In fact, you could make the sample as large as you want. Notice that this graph also can be used to answer some other questions such as: what is the likelihood of getting a sum of 11 or more? Or 10 or more? Or less than 3? Or getting a sum of 6? Or a sum between 4 and 8? Now, let's change the simulation one last time for today. First, use a mixer instead of a spinner. Then, include values from 1 to 10. Then, run the simulation 100 times, just to make sure it is working right. Now, let's draw only once, and let's also switch from a mixer to stacks. stacks are a lot like mixers. But, with stacks, it's easier to change the number of items of each type. The sampler we've just made would not be fair, of course, because the chances of getting a 5 would be much better than the chances of getting a 1. And, there is no chance at all of getting a 10. So, let's change the sampler back to being a fair sampler. One way to see that it's fair is to switch the sampler back from using stacks to using a mixer. But, for what we'll do next, stacks are more useful. For this sampler that's now shown, suppose that we ran it 100 times. How many 1s would you expect to get? How many 2s? How many 3s? The answer to all of these questions is 10. This is because the chances of getting each number should be the same. So, if the sample is 100, and if there are 10 different possibilities which are equally likely, then we would expect to get 10 of each. Of course, we wouldn't expect to get exactly 10 of each, because the samples are being chosen randomly. But, if a really large sample were drawn, then we would expect for 1/10 of the sample to be in each category. So, let's check this by running the sampler 1000 times, and graphing the results to see how many are in each category. As you can see, even a sample of 1000 shows variation. But, if we run the experiment many more times, the expected number would still be the same for each category, in spite of variations that we know will occur. For example, suppose we ran the simulation 100,000 times. As the sample size gets increasingly larger, the real values get increasingly closer to the expected value. Sometimes, it is possible to estimate the likeliness of winning a game just by inspecting the sampler. For example, for each of the 3 games shown below, approximately how many times would you expect to win if you played 10 times? By now, you should be able to build a sampler like each of the ones shown below. So, do this now, only make the samplers so that the likeliness of winning is 80%. The probability of winning is equal to the total number of ways of winning divided by the total number of possible outcomes.